Hi boys and girls. In the last video we understood a half subtractor wherein we subtract two bits xn and yn and obtain the difference and borrow in that stage. That propagates to the next stage. That borrow propagates to the next stage. In this video we understand a full subtractor. It is very similar to a full adder except that instead of the carry input I have a borrow input. So in one full subtractor circuit we subtract two bits xn and yn and borrow from the previous stage bn minus 1. So I subtract xn, I make the operation xn minus yn minus bn minus 1 to get a difference bit dn and the borrow in the current stage, or borrow that is to be propagated to the next stage, borrow output. So let me start with that presentation. So the speech is organized into your learning outcomes, then the circuit of a binary full subtractor and its design, then the full subtractor with integrated circuits, then full subtractor on Verilog, and finally summary of what you learned. So what you will learn in this video is that you will learn the theory of binary subtraction with a full subtractor and you will design a full subtractor. Then you will learn to implement a full subtractor in QUCS and in Verilog. Then you will appreciate the wiring diagram for a full subtractor with the medium scale integration chips. A full subtractor subtracts two bits xn and yn and previous borrow bn minus 1. So you remember how the binary subtraction happens. You subtract these two bits. Suppose I subtract a 0 from a 1 or 1 from a 0, there is no 1 from a 1. You don't need any borrow. But if you subtract a 1 from a 0, you need to borrow a bit from the left. So that is a borrow bit. So what a full subtractor subtracts is it does an operation xn minus yn minus bn minus 1. That produce the difference bit dn and borrow output. So that stage has input xn, yn and bn minus 1, and the outputs are the difference bit dn and the borrow bit bn. So that truth table looks like this. Suppose xn, yn, bn minus 1 are the inputs. So dn is the difference output and bn is the borrow output. So for the 3-bit pattern, I can have 8 possibilities like a 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1. Now for the case 0, 0, 0, the difference is 0 minus 0 minus 0, that's a 0, and the borrow is also a 0. I don't have to borrow anything. Here the difference is 0 minus 0, that's a 0. 0 minus 1 is a 1 with a borrow 1. Since I am subtracting 1 from 0, I need to borrow 1 bit from the left. So the difference is a 1 and the borrow is a 1. Then I consider this case 0, 1, 0. When 0 is subtracted from 1, the result is a 1 and the borrow is a 1. This 0 is subtracted from this 1, making the difference of 1 and the borrow 1. And here it is 0 minus 1, it is a result is a 1 with the carry borrow 1, and that difference 1 is subtracted. This 1 is subtracted from the difference, making the difference 0 and the borrow 1, because in this stage I had a borrow 1. 1 minus 0 is a 1, minus 0 is a 1, that is difference is a 1 and the borrow is a 0. Here 1, 0, 1, it is 1 minus 0 is a 1 minus 1 is a difference is a 0 and the borrow is a 0. Then 1 minus 1 is a 0, minus 0 is a 0, or difference is a 0, borrow is a 0. When it is 1, 1, 1, when I subtract 1 from 1, it is a 0. When I subtract 1 from that 0, or 0 minus 1 becomes, the difference becomes a 1 and the borrow becomes a 1. Now I have to put these two values in the truth table. You can see that by observation, you can see that this dn is same as the sum in the case of a full adder. This difference is the same as the sum in the case of a full adder, which is nothing but xn XOR yn XOR bn minus 1. But Bn is slightly different, so I had to put these things, these two into Karnaugh maps and solve for Dn and Bn. So here I make a Karnaugh map like this. This xn and yn, they are the MSBs, and Bn minus 1 is the LSB. So I put these values like this. This is a 0 1 1 0 1 0 0 1 0 1 1 0 1 0 0 1. Now you can see the corner adjacencies. This is actually an exclusive, or even without this you can know, because if you compare this with the truth table of a full order, you can see that this Dn is nothing but xn XOR yn XOR Bn minus 1. You can refer to that old came up and truth table. This, or else you can understand this corner adjacency, and you can see that it is an XOR Bn, xn XOR yn XOR Bn minus 1. So the difference Dn is Dn xn XOR yn XOR Bn minus 1. That is equation 1a. Understand equation 1a. This is the same as that of the sum of a binary full order. Sum of a binary full order. The difference of a difference is also an identical function. But the borrow is different. That's how they differ. So how is the borrow coming? I have 0 1 1 1 0 0 0 1. 0 1 1 1, then 0 0 0 1, 0 1 1 1 0 0 0 1, 0 1 1 1 0 0 0 1. You can see that in this there are three pairs. One is this red pair, one I mark in red oval. What is that? That corresponding function is, it is 0 1. This is Bn minus 1 is changing. It is flipping from 0 to 1, so it's not a function of Bn minus 1. Here it is 0 1, so it is xn and yn. So the first term is xn and yn, one mean term is xn and yn. And here if you go into this blue oval, you can see that this does not does not vary in this is a function of Bn minus 1 because it happens in one row. So it is Bn times, here what does not change is xn complement. Okay, what does not change is 0 0. That is xn complement. So it is bxn and Bn minus 1. Sorry. It is xn bar and Bn minus 1. Xn bar and Bn minus 1. That is the second time, xn bar and Bn minus 1. Now I come to the violet oval. You can see that's a function of Bn minus 1. Here what does not change is yn. It is Bn minus 1 yn and Bn minus 1. Okay. So equation 1b gives you the equation for Bn, that is xn bar yn or xn bar Bn minus 1 or yn and Bn minus 1. Okay. So the circuit looks like in figure 2, that is here. Here you can see that this is xn bar. This is my difference, that is xn XOR yn XOR Bn minus 1. Xn XOR yn XOR Bn minus 1. This is my difference bit. Okay, this is identical to the sum bit in a full order. But the borrow is different. Here it is xn bar. This is this gives me this, and output gives me xn bar yn, and this gives me xn bar Bn minus 1. This AND gate gives me xn bar Bn minus 1, and this is yn and Bn minus 1. These three are rolled together to get a bit. What is that bit? That is a borrow bit. So this is my borrow. This is xn bar yn or xn bar Bn minus 1 or xn yn and Bn minus 1. Okay, or yn and Bn minus 1. So that is my Bn. So this is how my circuit looks like. Now this circuit, I have designed this circuit. Now I can simulate this circuit in QUCS. So let me go to that simulation. If you come here, I have made a full subtractor like this. Okay, I made a sub circuit of a full subtractor because I will be using this full subtractor to make not only a 1-bit full subtractor, but I will be making a 4-bit parallel subtractor of that. So wisely I make it into a sub circuit so that I can drop these blocks wherever I need. I can drop these blocks and connect and design the circuit or develop the circuit. So here you have these three inputs, xn, yn and Bn minus 1. This is my sum difference bit, that is xn XOR yn XOR Bn minus 1. This is xn bar, this is my y, this is xn bar y, and this is my xn bar Bn minus 1, and this is my yn Bn minus 1. These things are rolled together. to get my borrow output. So this is my I will show this is my difference, and this is my borrow bit. Now I can drop this in another figure. I can drop this block. If you this block is my sub circuit. I will go into that sub circuit for your verification. If I go into the sub circuit, you can see that this is the same circuit. Okay, I encapsulate this full subtractor in a block with the pins 1, 3, 5. They are for xn, yn, and bn minus 1. If you look here, you can see that these are the pin or port 1 for xn, port 3 for bn, and port 5 for bn minus 1. Sorry, this is for bn. Yn, this port 3 is for yn, and port 5 is for bn or bn minus 1. And this port 2 is for difference, and port 4 is for the borrow out. So here what I do is I give 3 signals here. This is a 1 nanosecond, 1 nanosecond pulse. This is a MSB, this is a LSB. Borrow in is a LSB. This is a next bit, yn is a next bit. This is a 2 nanosecond pulse. This is a this MSB, this is a 4 nanosecond pulse, and I drop in a digital simulation with the model Verilog, and I put a time list or whatever. Then I run this code, I run this simulation to know my truth table. So here you can see this truth table. Here you can see that xn is 0000001 to say 111. You can see that it's in agreement with my earlier truth table. When it is 000, difference is 0, borrow is 0. When it is 001, difference is 1 and the borrow is 1. When it is 010, it is 0 minus 1 is a borrow is a 1, and that 1 minus 0 is a 0, difference is a 0. Then 0 minus 1 borrow is a 1, and bit is a 1, so 1 minus 1 is a 0. Then 1 minus 0, 1 0 0, it is a 1 0. 1 minus 0 minus 0 is a 1, and the carry is a borrow is a 0. 1 minus 0 minus 1 is effectively 1 minus 1, that difference is a 0, and borrow is a 0. 110 is again 1 minus 1 minus 0, that is equal to, the difference is 0 and the borrow is 0. Now when it comes to 1 minus 1, it's a 0, 0 minus 1, but difference is a 1 and the borrow is a 1. So that verifies my circuits, that verifies the truth table. So I can use this block in other circuits. I can use the same circuit in same sub-circuit in other 4-bit parallel ladder, etc. So you at home, you develop the circuit in QUCS and appreciate this. Now let me go back to my presentation. I have this presentation here. So now I want to have this full subtractor on IC. So what I can do is I need, if you go to the lab, you can get these MSI or LSI chips. What you get here, one here is an exclusive OR gate. So you can use a 7486. It contains 4 exclusive OR gates. Those 3 exclusive OR gates can be used for making this circuit. You can connect 2 exclusive OR gates to form a 3-bit exclusive OR, because exclusive OR is an associative function. So you can make with that you need a 7486. Then you need a 7432, because you will be needing the 7408 and gates are needed. So you need 3 AND gates here. So you can use a 7408, which is an AND. The 7408 is an AND. There are 4 AND gates in that. You need 3 AND gates, and you need one more chip, that is 7432. That's an OR. Okay, this is an OR. So I need a 7432. Then I need an inverter. Either you can put a new inverter, a chip like 7404 or something, or it's you can make, because you are an exclusive circuit, exclusive OR circuit here. You usually 3 of these gates. Okay, you usually 3 of these gates. You have one spare gate there, so that you can convert to an inverter. How do you convert an exclusive OR gate into an inverter? To input exclusive OR into an exclusive OR gate into an inverter, you tie one of the bits to high, logic high, and apply the signal in the other input. So if it is X, the output will be X complement. So you can use one of the exclusive OR gate as an inverter. So you need an exclusive OR gate, a 7486 gate, an AND gate, that is 7408, and an OR gate 7432. Okay, so that circuit will look like this on board. If you will have a circuit like this, Here you can see that I have three lines x and y and bn minus 1. This you can realize in your breadboard or PCB or something, and you can connect them to toggle switches or pattern generator or whatever you have in the lab. And here you can see that you have the 7486. This is a 4 quad 2 input exclusive OR gate. I use these two to form a the difference. That is, I apply xn here, yn here. So this output is xn XOR yn, and this is XORed with bn minus 1. So this series connection, this cascade gives me xn XOR yn XOR bn minus 1, which is my dn output. This I connect to a normally on LED through a 220 ohm resistor. Okay, the supply, ground, everything should be made. First you have to connect the ground, and then you have to connect the supply and everything. That goes without saying. Now we have to make an inverter, because you need X bar. Okay, so what I do here is this 5 volt thing, it comes to this IC. Along with that, it goes to input of a one exclusive OR gate, making this an inverter. This acts like an inverter. Okay, so here you can give to the other input, I give my X, so that this output is my X complement. This output at pin 3, that is my X complement. This X complement is ANDed here with yn. Okay, this X complement is ANDed with my bn minus 1. Okay, bn minus 1. So these AND outputs are then ORed. Okay, these AND outputs are then ORed, because this output is taken here, this output is taken here. Okay, then I need a 3 input OR gate, so I use 2 OR gates to form a 3 input OR gate, because OR gate is an associative function. So output of the first OR is connected to the OR input of the second OR gate, then to which I give this input. What is this? This is my bn minus 1 yn. This is my bn minus 1 and yn. This and output comes here. So this point, this sixth point is my difference. Sorry, this is my borrow. The sixth pin is my borrow. So I connect an LED there, and either I apply toggle switches here in xn and yn and bn minus 1, and manually you turn on these toggle switches and apply the pattern 0 0 0 to 1 1 1 and verify this output. Now you have to implement this full subtractor on Verilog. It is very easy, because we have seen the circuit. What I need is, I need the basic gates only. So I actually modified the other one, the full adder, and made it into a full subtractor. I start the module, say F sub. Okay, module F sub, some output wire. What are these outputs? Difference is one output, borrow output. Here I change some names, that's all. Difference is dn is my difference, then borrow output, these are the outputs. And what are the inputs? They are wires, they are x, y and b in. X, y and b in, but borrow in, or the previous borrow. These are the xn and yn bits. This is the bn minus 1. Now I need I have some internal nets, like outputs of some gates are to be connected to the next gate, etc. So here I define some wires, wire interdiff. This is for this is the output of the first exclusive OR gate. Okay, so the intermediate difference, then A, B, C, D, some values I have given. So first I make the difference. First I use a 2 input. I realize this just like that circuit. So for your understanding, XOR one gate, I say N1, this is an XOR gate, the output is interdiff XY. So at first XY are given to this, and output is interdiff. Okay, so to which in the second exclusive OR gate, that is N2, I apply this interdiff along with my bin, so that I get the difference. So this difference is nothing but xn XOR y XOR bin, x XOR y XOR bin. Okay, so output of this together, these two XOR get together, this forms my difference bit. Then I need an inverter, so x should be inverted, so I use a NOT gate in 3, that is x and a is x complement. Now I have three AND gates. First AND output is a comma y, okay, because this is x bar y, okay, x bar y. Then I have x bar b in, okay, x bar b in, that output is c. Here this output is b. Then and then a third AND operation, that is b in and y and b in, that gives me say d. So then I use two OR gates, because a 3 input OR gate, like I need to OR B, C and D. So BC I first OR to get E. This E is ORed with D to get my borrow output. Okay, so then it ends module. And we will run this code with iVerilog. Name of the file was fsub. This is my fsub.v. This is the file you have seen. Then I have an fsub tb. Okay. Now this is my device fsub. This device we were discussing the Verilog code for this file, in this file. So this fsub is there. Then I make a test bench for this. I actually modified the full adder. Okay, here I make a subtractor. Okay, I modified the full adder slightly. Here I have to include my fsub.v. This is a device under test. Okay, then some module test bench, xy, some borrow in. They are the registers, they are the input. Output is a wire difference and borrow out. Okay, so then I make an instance of the subtractor, full subtractor, that is fsub some y1 some value, diff borrow out x comma y comma borrow in, x comma y comma borrow in. That makes an instance of the full subtractor. Then as usual I give the monitor and everything. I initialize this things. I write to some dump file fsub.dump, and I give these patterns. All these patterns are given like a 0 0 0 0 0 1, that way. Then I finish and end module. Now we can run this code and appreciate this. I will enhance it a little so that you can view that. Now I can say iVerilog fsub .v. Now I can run this test bench iVerilog tb.v -o a.out. Now both files are compiled without a problem. Now I have to run this executable, that is a.out. Now you can see the truth table. Initially at 0 nanosecond they are all in indeterminate state. At 10 nanosecond you can see that 0 0 0 the difference is 0, borrow is 0. When it is 0 0 1 the difference is 1 and the borrow is 1. When it is 0 1 0 you can see that the difference is 1 and the borrow out is 1. When it is 0 1 1 you can see that the difference is 0 and the borrow out is 1, because it is 0 minus 1. It is a 1 with a borrow 1. That 1 is subtracted from this, so that it becomes a difference is a 0 and the borrow is a 1. Now here it is a 1 0 0. It's a 1 minus 0 minus 0. The difference is a 1 and the borrow out is a 0. Then I have 1 0 1. Again it is 1 minus 1. That difference is 0. Borrow is a 0. Here it is 1 1 0. It is 1 minus 1. So the difference is 0 and the borrow is 0. Here it is 1 1 1. Last case 1 1 1. Here it is 1 minus 1 is a 0. 0 minus 1 is a difference is a 1 and the borrow is a 1. So that means the device is working correctly in Verilog. Well, let me go back to my presentation. So you can develop this code at home and you can verify these operations. Now coming to the end, what you learned in this video is that you learned the theory of binary subtraction with a full subtractor, and you designed a full subtractor with two Karnaugh maps. Then you learned to implement it in QUCS. So you made a sub-circuit with a sub-circuit of a full subtractor, and you embedded it in a block, and you verified its truth table. And you keep it for further development. Then you develop this module in Verilog. Then you run the test bench, and you verified the truth table. Then you understood the wiring diagram of a full subtractor with the integrated circuits like 7486, 7432 and 7408. And that is the end of this presentation. I thank you all.